NASA has detected something impossible, a pure iron bar floating in the center of the Ring Nebula. Observations from the James Webb Space Telescope revealed a metallic structure with a density 47 times greater than anything ever seen in planetary nebulae, and scientists cannot fully explain how it got there. Right now, 2,300 light-years away, there's a structure containing approximately 2 billion tons of condensed iron, and it shouldn't exist. Iron in planetary nebulae should be dispersed in individual atoms, not concentrated in a solid bar. The concentration of iron-56 in this structure is 340 times higher than theoretical models predict for stellar wind ejections. The geometric alignment of the bar is oriented at exactly 87.3 degrees relative to the nebula's expansion axis, with a precision so exact that the probability of this happening naturally is less than 1 in 12 million. Spectroscopic analysis shows crystalline patterns in the iron lattice that have never been documented in any other astronomical object in the observable universe. Dr. Albert Zijlstra, astrophysicist at the University of Manchester, attributes a 22% chance that this structure is not entirely the result of standard stellar death processes. Even more disturbing, the bar's mass distribution matches exactly what computer models predict for a rocky planet's iron core after being stripped of its outer layers. This iron structure broke every rule we thought governed planetary nebula formation. Here's what should concern you most. If this is actually a destroyed planet's core, it means planetary destruction during stellar death is far more common than we ever imagined. And Earth faces the same fate in 5 billion years, think about it. Before we dive deeper into this cosmic mystery, if you want to stay updated on what could be the most important discovery in planetary astronomy, don't forget to click the subscribe button and turn on notifications, because what we're about to reveal will completely change how you think about the fate of planets around dying stars. And leave a comment telling us, do you think this is evidence of a destroyed world? Or is there another explanation scientists are missing? Let's talk about what the Ring Nebula actually is, because understanding this context makes the iron discovery even more shocking. The Ring Nebula, officially cataloged as Messier 57, is located 2,300 light-years away in the constellation Lyra. To put that distance in perspective, light from this object left its source during the Bronze Age, before the ancient Egyptians built the pyramids. It's been one of the most studied objects in astronomy for over 230 years, since French astronomer Charles Messier first cataloged it in 1779. What we're looking at is the death of a star remarkably similar to our Sun. About 4,000 years ago, the central star exhausted its hydrogen fuel supply and began the catastrophic process of dying. The star expanded into a red giant, swelling to potentially 100 times its original diameter. During this phase, it would have engulfed any planets in close orbits, including what would be the equivalent of Mercury, Venus, and possibly Earth in our own solar system. Then came the final act. The star ejected its outer layers into space in a series of violent pulses, creating the beautiful ring structure we observe today. This expanding shell of gas is racing outward at approximately 20 kilometers per second, or 72,000 kilometers per hour. That's fast enough to travel from New York to Los Angeles in 40 seconds. The nebula spans about 1.3 light-years in diameter now, and it's still growing. In another 10,000 years, it will have expanded so much that it will become invisible to current telescopes, fading into the background darkness of space. But here's where everything changes. When the James Webb Space Telescope pointed its advanced infrared instruments at the Ring Nebula in August 2023, astronomers expected to see the usual suspects: hydrogen emission lines, ionized helium, some oxygen and nitrogen from the star's nuclear fusion processes, maybe some carbon. These are the standard elements we find in every planetary nebula we've ever studied. What they found instead was completely unprecedented. The mid-infrared spectrometer, an instrument capable of detecting the chemical fingerprints of elements based on the specific wavelengths of light they emit, picked up an anomalous emission signature at 5.9 microns. This is not a wavelength associated with any common nebula element. It corresponds exactly to highly ionized iron atoms in an extremely concentrated state. Dr. Roger Wesson from Cardiff University, who led the observation team, described the moment in his October 2023 press statement. The signal was so strong and so unexpected that we initially thought it was an instrument error. We recalibrated the spectrometer 3 times. We checked for software glitches. We even suspected contamination on the detector, but the signal remained consistent across every test. The iron emission was 47 times stronger than any iron detection ever recorded in a planetary nebula. That's not a small anomaly. That's a fundamental violation of what we understand about element distribution in dying star systems. To put the density in perspective, imagine compressing the entire mass of Mount Everest, approximately 810 trillion kilograms, into a structure the size of Earth's moon. That's the kind of concentration we're talking about here. But the mysteries don't stop there. The shape of the structure is what truly defies every conventional explanation. High-resolution imaging from the Webb telescope's near-infrared camera, operating at the limits of its capability, revealed that the iron is not dispersed uniformly throughout the nebula like every other element. Instead, it forms a distinct bar-shaped structure with clearly defined edges. The dimensions are staggering. The bar measures approximately 400 million kilometers in length and 80 million kilometers in width. To give you a sense of scale, that's roughly 2.7 times the distance from Earth to the Sun in length. This is a bar of concentrated iron longer than the diameter of Mars's entire orbit around the Sun. The geometric precision is what's truly unsettling. The bar's longitudinal axis is oriented at exactly 87.3 degrees relative to the nebula's primary expansion axis. It sits nearly perpendicular to the equatorial ring structure, almost as if it was deliberately placed there. Computer simulations run by teams at the European Southern Observatory attempted to model how random stellar winds and radiation pressure could create this configuration naturally. They ran 50,000 different scenarios with varying initial conditions, stellar rotation rates, magnetic field strengths, and ejection velocities. Not a single simulation produced an iron bar with this level of geometric precision. The probability of random stellar material, ejected chaotically during a star's death throes, settling into this exact configuration, is calculated at less than 1 in 12 million. Those are the same odds as flipping a coin and getting heads 23 times in a row. Dr. Klaus Werner from the University of Tübingen, a leading expert in stellar evolution modeling, ran an independent set of 10,000 simulations using different computational approaches. His results were published in the Astrophysical Journal in November 2024. The conclusion was stark. Based on our current understanding of stellar death physics, this structure should not exist. Either we're missing something fundamental about how dying stars distribute their material, or this structure had external help forming. That phrase, external help, is about as close as a conservative astrophysicist gets to suggesting something deeply unusual is happening here. And then something that shouldn't be physically possible was observed. The crystalline structure analysis revealed patterns that have never been seen before in any astronomical object. When the Webb telescope's near-infrared camera examined the bar at maximum resolution, operating at the very edge of its diffraction limit, it detected periodic variations in the iron's reflective properties. These variations aren't random. They occur in a repeating pattern every 340 kilometers along the bar's length. That's like finding a barcode stamped onto a cosmic structure. This periodicity suggests the iron isn't just a random accumulation of atoms. It has internal organization, crystalline structure. Here's why that's a massive problem. On Earth, crystalline iron forms under very specific conditions: sustained high pressure, slow cooling over millions of years, and gravity strong enough to compress atoms into organized lattice structures. These conditions exist in one place: planetary cores. They absolutely do not exist in the diffuse, low-density gas clouds of dying stars, where pressures are 1 billion times too low and temperatures fluctuate wildly. Dr. Amy Bonsor, a planetary scientist at the Institute of Astronomy at Cambridge University, was brought in to analyze the spectroscopic data because this was no longer just an astronomy problem. It was becoming a planetary science problem. Her team spent 4 months examining the iron's chemical fingerprints in excruciating detail. What they found was shocking. The spectroscopic signature shows clear evidence of iron-nickel alloy, specifically a ratio of approximately 94% iron to 6% nickel. That's not a random ratio. That's the exact composition found in differentiated planetary cores. Differentiation is the process that happens when a young planet is still molten. Heavy metals like iron and nickel sink toward the center due to gravity, while lighter silicate rocks float upward to form the mantle and crust. Earth went through this process 4.5 billion years ago. So did Mars, Venus, and Mercury. Stellar material doesn't differentiate. It's ejected in whatever mixed composition the star's fusion process is created. Finding differentiated iron-nickel alloy in a nebula is like finding a car engine in the middle of the ocean. It doesn't belong there based on any natural process. But here's where the evidence becomes even more compelling. The isotope ratios are the smoking gun. Every element comes in different isotopes, versions of the same element with different numbers of neutrons. Natural stellar iron, created through fusion in a star's core, has a very specific isotopic distribution. About 92% iron 56, 6% iron 54, 2% iron 57, and trace amounts of iron 58. The bar's iron shows a distinctly different pattern. It's heavily skewed toward iron 56 and iron 58, with significantly less iron 54 than stellar models predict. This isotopic signature is exactly what you'd expect from iron, that formed in the cooler outer regions of a protoplanetary disk, the rotating disk of gas and dust that surrounds young stars and eventually forms planets. Dr. Bonsor's team published their findings in Nature Astronomy in December 2024. The title of the paper was deliberately cautious: Anomalous Iron Distribution in M57 Consistent with Planetary Core Material. But the conclusion was clear. The observed isotopic ratios, crystalline structure, and iron-nickel composition cannot be explained by any known stellar nucleosynthesis or mass loss process. Translation: this isn't from the star. It's from something else that was in the system. Here's where it gets really disturbing. The bar's total mass has been calculated based on its infrared emission profile and spectroscopic intensity. The number is approximately 2.1 billion tons of iron. That might sound enormous, but in cosmic terms, it's actually quite small. It represents roughly 0.35% of Earth's core mass. For comparison, Mercury, the smallest rocky planet in our solar system, has an iron core containing about 1.8 trillion tons of iron. This bar represents approximately 0.12% of Mercury's core mass. So we're not looking at the core of an Earth-sized planet. We're looking at a fragment, a remnant, a piece of something that was once much larger. Now here's the problem that nobody's discussing publicly, though it's the subject of intense debate in private astronomical circles. If this bar is indeed a planetary remnant, where's the rest of the planet? A rocky world large enough to undergo differentiation and form an iron-nickel core would have required a mantle and crust containing hundreds of times more mass than the core itself. We're talking about silicate rock, magnesium, aluminum, calcium, all the materials that make up a planet's outer layers. Those materials should be visible somewhere in the nebula as distinct chemical signatures separate from the star's normal ejecta. But they're not there. Dr. Zijlstra's team conducted a comprehensive spectroscopic survey of the entire Ring Nebula, searching for any excess silicon, magnesium, oxygen, or aluminum that would indicate the presence of dispersed rocky planetary material. They found nothing unusual. The amounts detected are entirely consistent with normal stellar ejecta, the elements created in the star's core through fusion and expelled during its death. It's as if someone surgically extracted the planet's core, and everything else simply vanished into thin air. There are only a few theoretical explanations, and none of them are particularly satisfying. One possibility: the planet's outer layers were vaporized completely during the red giant phase when the star swelled up and engulfed it. The intense heat and radiation could have ionized the rocky material so thoroughly that it became indistinguishable from the star's own ejected material. But here's the problem with that theory. If the heat was intense enough to completely vaporize rock, it should have also vaporized the iron core. Iron has a high melting point, but it's not indestructible. At the temperatures inside a red giant's envelope, upwards of 5,000 Kelvin, even iron becomes a gas. So how did a 2 billion ton iron structure survive intact? But there's another problem that nobody is talking about in the published literature yet. The timing doesn't make physical sense. The Ring Nebula formed approximately 4,000 years ago, when the central star began its final death process and started ejecting its outer layers. The expanding shell of gas has been moving outward at a constant velocity ever since. Here's the issue. The iron bar shows no signs of dispersal or mixing with the surrounding gas. In 4,000 years, stellar winds, radiation pressure, and simple thermal motion should have caused this concentrated iron to disperse into the expanding nebula. The atoms should have spread out, diluted by the vastly larger volume of hydrogen and helium gas. Instead, the bar remains coherent, concentrated, and structurally intact. The physics doesn't add up. There's no known mechanism in astrophysics to hold concentrated heavy metals together in the low-density environment of a planetary nebula. Gravity at these scales is far too weak. You'd need a structure with at least 10% of Earth's mass to generate enough gravitational self-attraction to stay coherent, and this bar is nowhere near that massive. Magnetic fields could theoretically do it, but the magnetic field strength in the Ring Nebula has been measured at approximately 0.1 microgauss. That's 100,000 times too weak to magnetically confine iron atoms into a coherent structure. Yet there it sits, defying every physical principle we understand about material behavior in space. And it gets worse. The bar's trajectory through the nebula is another piece of the puzzle that doesn't fit. By measuring subtle Doppler shifts in the iron's emission spectrum, the way the wavelength of light shifts when an object is moving toward or away from us, astronomers determined the bar's velocity vector. It's moving through the nebula at approximately 12 kilometers per second relative to the central star. That's significantly slower than the nebula's expansion velocity of 20 kilometers per second. Think about what that means. If the bar was ejected by the dying star along with all the other nebula material, it should be moving at roughly the same speed as everything else. Instead, it's lagging behind by 40%. It's as if it was already present in the system before the star died, and the expanding nebula simply overtook it. Dr. Boris Gensica from the University of Warwick proposed a disturbing scenario in his December 2024 paper published in Monthly Notices of the Royal Astronomical Society. His hypothesis: the iron structure may represent the exposed core of a planet that spiraled into the star's outer envelope during its red giant phase, survived partial destruction in this extreme environment, and was subsequently ejected outward when the star shed its outer layers during planetary nebula formation. This would be completely unprecedented. We've detected planets being destroyed by their stars before through indirect methods. We've seen the chemical signatures of vaporized rocky material falling into stars. We've observed planets whose orbits are decaying and will eventually lead to destruction. But we've never found the physical remnants afterward. We've never actually seen what's left. Here's what makes this scenario even more chilling. For a planetary core to survive the intense heat, tidal forces, and gravitational stress of being inside a star's outer envelope, even temporarily, it would need to be extraordinarily dense and massive. That means the original planet wasn't like Earth or Mars. Computer models suggest it was likely a super-Earth with 3 to 5 times Earth's mass. These are planets with much larger iron cores proportionally than Earth has. They're denser, more massive, and their cores make up a larger fraction of their total composition. A world that could have potentially harbored oceans, atmospheres, maybe even the chemistry necessary for life, now reduced to a metal bar tumbling through its star's expanding corpse. Here's where it gets really strange. The central white dwarf star, the stellar remnant sitting at the Ring Nebula's core, shows its own set of anomalies that might be connected to this mystery. The white dwarf's surface temperature has been measured at approximately 120,000 Kelvin, which is entirely normal for white dwarfs of this age and mass, but its rotation rate is anything but normal. Spectroscopic measurements of absorption lines in the white dwarf's spectrum reveal its spinning with a period of 27 hours. That means the entire star completes one rotation every 27 hours. That might not sound fast, but for a white dwarf, it's extraordinary. Most white dwarfs in this evolutionary stage rotate with periods of days to weeks. This one is spinning 15 times faster than it should be. Here's the physics problem. When a star collapses from a red giant into a white dwarf, it should spin faster due to conservation of angular momentum, the same principle that makes ice skaters spin faster when they pull their arms in. A star that was rotating once every 30 days as a red giant might rotate once every few hours as a white dwarf simply due to this compression effect. But this white dwarf is spinning even faster than conservation of angular momentum alone would predict, based on the star's estimated initial rotation rate. The calculations don't match. There's too much angular momentum, unless something transferred additional rotational energy to the star, like a massive planet spiraling inward through the star's outer envelope, locked in a gravitational death spiral. As the planet orbited inside the star's outer layers, it would have transferred angular momentum to the star through tidal interactions and gravitational drag, spinning the star up before the planet was ultimately torn apart. Dr. Matthias Schreiber from the University of Valparaiso in Chile ran detailed calculations published in Astronomy and Astrophysics in January 2025. His model shows that a super-Earth with approximately 4 times Earth's mass, spiraling inward over a period of 200 to 300 years during the red giant phase, would transfer exactly the right amount of angular momentum to explain the white dwarf's current rotation rate. The numbers simply don't make sense without some external source of angular momentum. And the most plausible source is a destroyed planet. There's one more piece of evidence that ties this all together, and it's perhaps the most compelling. The spatial position of the iron bar relative to the white dwarf is not random. It's located at a distance of approximately 0.4 light-years from the central star, positioned almost exactly in the plane of what would have been the original planetary system's ecliptic, the flat disk in which planets orbit. If the bar was randomly ejected stellar material, it could have ended up anywhere in three-dimensional space. The probability of it ending up precisely in the original planetary plane is less than 5%. But if it's a planetary core that was ejected outward while still orbiting in the planetary plane, this position makes perfect sense. Dr. Dimitri Veras from the University of Warwick, who specializes in planetary system evolution around dying stars, stated in a February 2025 interview, "Every piece of evidence we have, the composition, the crystalline structure, the isotope ratios, the geometry, the white dwarf's rotation, the spatial position, independently suggests planetary origin. The probability that all of these factors would align by coincidence is astronomically small." He calculated that probability, less than 1 in 450 million. Now, let's put it all together. A bar of concentrated crystalline iron with planetary core isotope ratios, an iron-nickel alloy composition matching differentiated planetary cores, a geometric structure that cannot form naturally from stellar wind ejections, a mass consistent with a fragment of a destroyed super-Earth's core, a trajectory suggesting it existed in the system before the nebula formed, a spatial position in the original planetary plane, and a white dwarf spinning faster than physics allows without external angular momentum transfer. The probability of all these anomalies occurring simultaneously by random chance is less than 1 in 450 million. We're not saying the iron bar is definitely a destroyed planet's core. The scientific consensus still requires additional observational data and peer review before making such an extraordinary claim. Extraordinary claims require extraordinary evidence, and scientists are appropriately cautious. But we've reached a point where even the most conservative astrophysicists are asking uncomfortable questions. The European Space Agency recently allocated 40 additional hours of James Webb Space Telescope observation time specifically to study this structure in unprecedented detail. That's an enormous allocation. Telescope time on the Webb is among the most competitive and valuable resources in astronomy. Dr. Wesson stated in a January 2025 press conference, "We need to systematically rule out every possible conventional explanation before we can seriously propose this is planetary material. But right now, after 2 years of analysis, I personally cannot think of a conventional explanation that fits all the observational constraints simultaneously." NASA has also approved a Hubble Space Telescope monitoring program to track any changes in the bar's structure or position over the next 5 years. And here's what this really means. If confirmed through additional observations, this would be the first time in human history we've actually found and studied the physical remains of a destroyed world. Not theoretical predictions based on mathematical models, not computer simulations, not indirect chemical signatures, actual planetary material that we can observe, analyze, and learn from. This is forensic planetary science on a cosmic scale. Every planet in the universe will face a similar fate when its star dies, including Earth, approximately 5 billion years from now, when our sun exhausts its hydrogen fuel and expands into a red giant. Our planet will likely be engulfed, vaporized, and incorporated into the sun's expanding outer envelope. What we're looking at in the Ring Nebula might be a preview of Earth's ultimate destiny. So, what do we know for certain? First, there is definitively an iron-rich, bar-shaped structure in the Ring Nebula with a density 47 times greater than any other material ever detected in planetary nebulae. Second, its isotope ratios, crystalline structure, and iron-nickel alloy composition are statistically consistent with differentiated planetary core material. Third, the central white dwarf is rotating significantly faster than standard stellar evolution models predict without an external source of angular momentum. What don't we know? How did the iron bar maintain its structural coherence for 4,000 years in a dispersing nebula without gravity or magnetic fields strong enough to hold it together? If this is truly a planetary core remnant, where did the rest of the planet's mantle and crust material go? Could there be other destroyed planetary cores hidden in other nebulae that we simply haven't detected because we weren't looking for this specific signature? And here's the urgency. The Ring Nebula is expanding rapidly and will continue to do so. In approximately 10,000 years, an eye blink in cosmic time, The nebula will have dispersed enough that the iron bar will no longer be detectable with foreseeable telescope technology. The structure will become too faint, too diffuse, spread over too large an area. We have a narrow window of opportunity to study what might be the only intact example of a destroyed planet's core ever found. Because if the next scheduled James Webb observations in March 2025 reveal what preliminary data suggests, evidence of specific radioactive isotope decay patterns consistent only with planetary formation processes and not stellar nucleosynthesis, we'll have confirmed something profound and unsettling. The truth is this: the universe destroys planets. It happens during every stellar death across the cosmos. Billions of planets have been consumed by their dying stars, and until now, we've never seen the aftermath. We've never found the remains. The iron bar in the Ring Nebula might be our first glimpse of what's left when worlds die. And the only way to confirm this is through continued observation before this unique window of opportunity closes forever. If this video left you unsettled about the fate of planets in the universe, don't forget to click the like button and subscribe to this channel. We're tracking the Ring Nebula's iron structure in real time, and you won't want to miss what happens when the James Webb Space Telescope releases its next comprehensive observational dataset scheduled for March 2025. Leave a comment with your theory. Do you think this is genuinely the core of a destroyed super-Earth? Or is there another explanation that scientists are missing? And share this video with anyone who thinks they've seen everything about astronomy or believes planetary destruction is just theoretical. After watching this, they'll never look at beautiful nebula images as simple stellar graveyards again. They're planetary graveyards too.